afternoon. So in the previous class, we saw an example, right, where the Stationovich and Ito integrals give quite different answers. And that example was nice because it shows the value of all the work we have been doing over the past few lectures in stochastic calculus. Right? So we took the example of the geometric random walk, which if you remember was if x is the variable, then dx is equal to not just dw, the Wiener process, but dw is 3 multiplied by x. Right? So dx is equal to x dw. So this means if I take random steps from the Wiener process, I multiply that step with my current state x. And in this system, the x is assumed to be taken to be always positive. It is supposed to model things like prices if you take the Ito version, or in physical space, a situation where the diffusivity somehow depends on your position in space. The diffusivity, of course, should be positive, right? So that makes sense that x is positive. Okay, so right from there we see that if we take the geometric random walk, okay, we can take two interpretations as we have been doing in this course. So one is the Ito, right, where it will be x dw and the increment is independent of x because x is sampled at the before I toss the coin and get the increment. In the Stationovich version, x will be taken at the midpoint of my time interval, right, but in the discretized sense, and therefore now the x that I use will depend on the increment in that time interval. Okay, so because of this, as you know, as we have been doing, we get two different answers. Importantly, the Ito version will immediately show you that it has zero mean by definition. Right? Every Ito SDE, the base variable in which you write the Ito equation has zero mean. Okay, so on average, you will not move in the Ito sense. Whereas in the Stationovich sense, first of all, we saw that regular calculus applies, so we can show that you get a distribution where the logs are going to take, the log of x will be doing a random walk. And but moreover, if we transform the Stationovich to an equivalent Ito, right, you see that you get an extra drift, which results in exponential growth of the mean, right, as well as the variance. So both versions, Ito and Stationovich, show you exponential growth of the variance, but the mean is zero in Ito, whereas the mean is non-zero. In fact, it grows exponentially in the Stationovich. Okay, so this find we did by using the rules of calculus. But now, what we're going to do today is to say, okay, fine, I did all this formula stuff, but I want to actually see it happening, right, in some system. How do I know that all the stuff we've been doing is correct, right? Can I see an example? So that's what we're going to do today. Okay. Now the basic problem is that in doing an example, right, is we are taking the white noise limit, and this is not a real thing. Correct. So that's why it's not easy to see. And we've done the mathematics in the white noise limit, but what we want to see is some actual realization of this. In particular, I've been saying from the beginning that Stationovich is of interest because it's used to model physical systems which are not actually white, right, where there is some highly fluctuating signal driving the process, and you are taking the limit of that fluctuation time scale going to zero. Then we should do Stationovich, is what I've been claiming. And the only argument I've given you so far is that, okay, if it's a normal ordinary differential equation, then regular calculus should apply, and that's the only Stationovich does that. As I had hinted that there is a formal proof as well. Okay, but that's what we're going to see today in an example. But to do this, I need to first construct some kind of highly fluctuating signal, but which is not this delta correlated Wiener process, it's just some function of time. Okay, and here there is a nice idea which has been put forth by Trefethen and co-workers called smooth random functions, and that's what we're going to explore today. So we'll be doing that with, I'll show you some code and some results later on, but first let's try to motivate the idea of what is a smooth random function. Okay, so what do we want to do? So imagine you have some function, right, and I want this function really to try to approximate that zeta. Right? So when I wrote in ODE form, in the beginning I had a Algebra equation. Right? So I was basically using this, right, in the non-rigorous way of saying, okay, I have a particle which is moving, whose position is getting tapped in the dissipative limit by some highly fluctuating force. Right? So if I want to replace this Wiener process, wide correlated time limit by something smoother which has some correlation but which is highly fluctuating. I need some function to plug in here, right? Some known function of time. And then I can just solve this ODE. And the idea would be to say if I take this function, so I want to replace this, right? But this is now a smooth function. Smooth meaning it has derivatives, right? And sufficiently smooth. It's not got this weird behavior. So remember zeta, if we want to start saying it more precisely, we saw that zeta must be delta correlated in time, and in any time its variance is infinite, right? And this whatever this thing is, it's not differentiable. That's why writing this only doesn't make sense, right? Okay, so leaving that aside, if I want to approach this funny limit, which ultimately we saw this needs me to use SDs, not ODs, I can start from some smooth ODE and make this f more and more oscillatory. Okay. And this I can do numerically. And the idea would be if I do this exercise, do I actually converge to the kind of SDE mathematics we've been doing? Okay. And in particular, if I can construct such a situation, I can pre-multiply with this x. And I can see, do I get the Ito answer or the Stationowich? Okay, so this is what we'll do. So first let us cook up some f. So just graphically, if I have, let me draw some f's. Okay, so I want them all to be zero mean, because I want this force to have zero mean. Okay. But I want it to fluctuate about the mean in some apparently random way. So for example, I can have some function, and then I could have a much choppier thing. Okay. This is what I wanted to have in mind. This is what we're trying to do. And I want to make it choppier and choppier and choppier, right? But one would think, okay, that, and I want to have some way to control how choppy it is, because then I can converge. So typically, there'll of course be different kinds of variations, but maybe the smallest typical variation here, I'm going to call lambda. And this lambda I want to take towards zero. If when lambda goes towards zero, I'll get the white noise limit, right? Because obviously, if you by saying lambda, it means if I zoom in, right, on scale lambda, right? So t to t plus lambda, then things will be smooth. Okay. So it's always smooth if you zoom in sufficiently. That's the nature of any physical process. It should go back to Brownian motion itself. It's a result of molecular bombardment. But if you zoom into molecular timescales, there is some molecule moving slowly. And even the bombarding action is not like a delta force or something. Right? There is some interaction. So you can keep resolving it, and in the end, you will have some well-refined physical process. That's the classical picture from which we're looking at things. Right? So that is the idea I have in mind. But then if I stay at the large scales, let's say 0 to 1, and I make lambda go towards 0, that's when I should start recovering what is effectively something converging to the Brownian motion. Now, Brownian motion is the exact zero limit, right? Where this kind of idea of convergence doesn't exist. That's why we have to remember, do that root dt business when we do the integration. Okay. Fine. So right now, let's set aside, let's forget about SDs for the rest of this lecture until the end, and just think of an ODE. But I want to solve an ODE like this for the position of some particle, okay, where this is in some dissipative limit, so inertia has dropped away. This is the viscous drag is equal to the applied force, okay, Newton's law. And this F I can prescribe some force. And I can prescribe a relatively slowly oscillating thing or an increasingly rapidly oscillating thing. And then will I get something like Brownian motion? Okay, so now mathematically, how can I start specifying these things? So if you see this as a time series, right, as a function in time, you can of course describe any arbitrary function in time using a Fourier transform. So if I go from minus infinity to plus infinity, I can just do a Fourier transform. For numerical purposes, we will take some finite length, right, 0 to capital T. In this, I can do a Fourier series, finite Fourier series. Okay. Now you can say, okay, if I use Fourier series, this function will always be periodic, right, which I don't want. Then for numerical purposes, again, if I want an aperiodic arbitrary function, let's say I'm interested in integrating 0 to t, I can generate this function 0 to n times t, some much longer time series, and chop out a portion. Then you lose the effect of the periodicity. Okay, one can show this more rigorously, that if you generate a time series 0 to t prime and you take a smaller part of it, 0 to t, anywhere in between, the effects of periodicity will get lost as t prime gets larger and larger compared to the t you want. It makes sense also. Okay, so I can do that. So let's not worry about the Fourier being periodic. Right? In the end, whatever piece I want to integrate over, so I'm interested on 0 to capital T, I can generate a much longer periodic signal and then take only the part I want. So then I'll lose that periodicity problem. Okay, good. So then I can do a Fourier series. And that will give me something oscillatory. Okay. So I want to construct f of t so an f of t, let's say 0 to capital T, okay. So in 0 to capital T, I want to prescribe this f of t and I want to use Fourier series. So Fourier series because, I mean, it's a basis, right? But it also gives me a way to control this length scale, right? So let's say for the moment I've got a nice single periodic function, which will be prescribed here. So I take something like sine 2 pi by capital T, and then I put something here, okay. This is a single Fourier mode, okay, with mode number k, right? The way I've written it, when t goes to capital T, I will be fully periodic. Okay, so one full wavelength, if you like, will be from 0 to t if k is equal to 1. If k is equal to 2, I'll have 2 waves and so on. So you can see that the wavelength here, right, of course, is 1 by k. Sorry, t by k. Correct. So if k is equal to 1, the wavelength, of course, I have time, right? So the time period, if you like, is till t. Right? Let me say time period. Of that oscillation, right? And then if it's 2, then it will oscillate at half the time, right? So the typical time scale of this function. But now if I, it's okay, so that's fine, but this is not very helpful, right? If I do this, I'll just get one nice sinusoidal mode. By making k larger and larger, I can shrink the time over which it is oscillating. I can increase the frequency, but it's not going to be random, right? If I just take one mode, I can have something smooth like this, and then if I make high k, I'll have something choppy, but it's completely periodic, right? This is not what I want. I want something random. So what I should do? What should I do? Right? So what I can do is, again, you think about this, right? If I have some crazy looking random signal, it just means there are many Fourier modes. If there's a nice regular oscillation, there are one or few Fourier modes. If there is very complicated signal, it means it's spread out in Fourier space. So to construct something like this, I need to sum up the Fourier series. That means I take different values of k. And I can start right from k equal to 1. So that will give me an overall variation. Then 2 will add more variations and so on. And the interesting thing is what will set this typical length scale will be the largest k I choose. Okay, so again, if you just think of 2 k values, suppose I take k 1 and 100. Right? So that means I write f of t is sine 2 pi by t 1 plus sine 2 pi with k equal to 100. Right? So just 2 modes. What will you see? You will see one nice oscillation. And then on top of that, I'll get something like this. Right? So you see that the smallest variation is happening associated with the largest wave number. Or if I want to know the time scale, right? So I should not call it time period now anymore. Right? The small time scale. Right? It will be capital T by 100. So if I zoom into capital T by 100, then I will see something very smooth. I will not see that choppy behavior anymore. So that's what I mean by the smallest time scale. So you can see that the smallest time scale gets set by the T over the largest k. Okay. So what I can do now is I can add up many Fourier modes. So now in this case, I have 2 clear features. But now I want something more random, or approaching random. So I add in all the Fourier modes, for example, from 1 to 100. So that will give me all kinds of variations. Right? And if I want it to be random, then their amplitude should be random, right? And the phases should be random. Instead of, so by phase I mean you can, if you want to generalize this, you will say sine blah 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 plus phi. Or you do sine and cos. So Fourier series can be either way in terms of sine with a phase, or you take sine and cosine and you add them, in which case again the amplitude of the sine and the cosine both should be random. Okay, so what we are seeing now from this intuition is I can construct something like this if I just take a Fourier series with random amplitudes for the sine and cosine modes. And the important thing that I want to control, remember in doing this, is I want to, of course the amplitude I can control by controlling their random modes, but I can set the mean and the variance. So if I take 0 mean for all the amplitudes, the signal will oscillate about 0 mean. If I set the variance of those coefficients of these different Fourier modes, I can control the amplitude of the oscillation. Okay? And but the more important thing for me is to be able to take the white noise limit, which I can do by taking this largest k. So I do sine 1 plus sine 2 plus sine 3, k goes 1, 2, 3, 5, and I truncate the Fourier series somewhere. Right? That truncation sets the time scale. So if I want to approach the white noise limit, I should take k larger and larger. I mean the maximum value of k, the maximum Fourier mode number should keep being increased. It's not surprising. This is why it's called white noise. Right? The white idea comes from light spectrum, right? So this is like a spectrum of Fourier modes. Just as you have different wavelengths, so different frequencies. Here I'm taking different wavelengths in the signal, right? And as I take if I include all wavelengths, that means k going to infinity, then I get white noise, right? All the wavelengths in the light spectrum. This is the logic. That's the idea from where white comes, because it has all Fourier modes. That's why it is delta correlated, because the time scale of correlation is going to 0 as the maximum wave number you are including in the series goes to infinity. Okay, so we are basically using just that idea. Okay? But in the end, you see, it's of course smooth because it's a sum of sines. It's infinitely differentiable.
So will white also mean all the amplitudes of all the wavelengths of the time scale is the same?
No, they'll be random, right? Otherwise, they will not be a random series. So white is about the correlation time, not about amplitude. So there's basically no temporal correlation. At the next instant, whatever number you see is completely uncorrelated to the previous thing. This is what we have said, right? That's what Einstein started. And to construct such a thing or to approach that, this is what one has to do. Right? That's why it's called white, because of this connection. So in other words, if you generate, of course, it's something you cannot generate on a computer, right? Because you will take some delta t. So even in the Wiener process, I take some delta t. If I construct such a series and then I do a Fourier decomposition, I'll get all the frequencies precisely up to k, the largest k, which is the floor of capital T by delta t. So I take capital T divided by delta t, I'll get some very large this thing. If I round it to the integer from below, that is the k. Yeah, but that's because I discretized it. So then I should not consider higher modes. But I can of course keep resolving the Wiener process. So the equivalent of fixing the delta t in a numerical realization of any Wiener sampling, right, is fixing the k here. What we really have in mind is I want to take, but the nice thing here is I can take that k to infinity, okay, and at any finite k I have a nice smooth function for which I have just an ODE. The mathematics is the same mathematics of ODEs. So for example, I can plug in, I take some large value of k like 100 or 1000 or whatever, I put it here, I can just solve this equation using any ODE solver. If it just, I can just directly integrate this is simple. But if I pre-multiply with x square, whatever, I can use some Rangikuta and do it. I just have to take very small time steps, obviously. But in terms of mathematics, it's just an ODE, which will have a unique solution because f is something smooth for any finite k. Okay, so let me now give you write down the formula for this f. So I'm summing now over k from 1 to m. So m is the maximum mode number I'm taking, right? I want a1 cos AK, BK, right? So this AK and BK are coefficients, right, which will keep changing. Sine sorry? Sorry, correct. Thank you. Very good. Okay. So this is just the formula for what we've been saying. Okay. And the important thing is I'm truncating at m. Okay. So now if I want, so T is, so the domain, if you like, okay, is 0 to T. I want to define the function. And the time scale lambda, okay, is what I want to choose. So then m, okay, is, this is a symbol for floor of T by lambda. Okay. Or I'll just write it. Okay, so that means you take T by lambda. If it's 100 and 100.2, then 100 is m. It's the closest integer. That is less than or equal to this number ratio. Okay, because I want to set m such that I get the lambda that I want. Okay, the idea is now as m is increased, lambda will decrease. Okay, and lambda is directly this time scale. And white noise is when lambda is 0. Okay, now the important thing is what are these AIs, right? So this AK, comma BK, right, are both from Gaussian distributions, right, with 0 mean. Okay, now we come to the important, some details. Okay, so the main important point I want you to remember is I'm going to sum a Fourier series, okay, with random coefficients, where I can control the smallest length scale by choosing the cutoff mode number, right, m. So that immediately gives me the smallest wavelength, smallest time scale. Okay. Now the rest are details, okay, which are explained in that, in what I will show you a reference in a second, okay, by Trefethen. But it's not too difficult to understand. So what I can now, definitely I want all the A's and B's to have 0 mean. Right? If they don't have 0 mean, then this F will not have 0 mean. And what I really want to do is I want F to start mimicking the Wiener process as lambda goes to 0. Okay, this is important. So then if I want F to have 0 mean, certainly all the A's and B's should have 0 mean. Okay. Again, because the Wiener process ultimately will have Gaussian statistics, I want these A's and B's also to be Gaussian. Okay. The important thing is now what is the variance that I have to decide. So if I take a bigger variance, the oscillations of this thing will typically be larger and larger. Okay, that's how I can control the size of the oscillation. Now what I usually want to do again is to represent this normalized Wiener process, right? Because I can always multiply in my, let's say I'm solving an ODE, right? dx dt is equal to some deterministic stuff plus some function into this f. This is what I want to do. Okay. So I can always multiply f by 10 or something or whatever number I like. Right? So I would like to create an f that is somehow normalized to unit variance. So what I want to do is get an ultimate f which has unit variance and 0 mean. To do that, I need to accordingly choose the variances of these things. Right? So I cannot take unit variance for each A because I'm summing up many of them, the variances will add up. Right? So remember, if there are random numbers and you add up the variance of the random number, which is the sum of other Gaussian numbers, will have the sum of the variance. Right? So I need to compensate for that. So I'll take variance 1 upon 2m plus 1, right? Because there are 2m plus 1 guys. Okay, there's a m, and there's extra one. So remember, this is the variance, not the standard deviation. The standard deviation is root of that. Okay, in addition to this, some extra subtle normalization things are there, but which can be worked out. There is also a root 2 factor that is placed in front of this, so that you get the correct properties in the end. I won't go into these. These are small details, which again, it's a matter of normalization, right? So it's okay. But this is clear to see, right? So I want, they are not unit variances, they are divided by the total number of these coefficients. Okay, so this f of t is what is the smooth random function. But so this is useful as a representation of some signal which you can of unit variance, right? Random, that I can then, and it is truly random. It's not apparently random, right? I mean, as long as if these A's and all are truly Gaussian random numbers, it is a random thing. Its value at any point is a sum of random numbers. What is an approximation is that it is not white, it is smooth in time. So it is time correlated random series, which is actually very nice because for many processes, you may actually want physically to introduce some time correlation and see okay, what is the effect of a correlated time scale on my physical system. Then this gives you a nice way of controlling that also. So today I'm going to use it to show you how the mathematics of the delta correlated limit work out, right? But in general, if I'm doing some modeling, the zero correlation time is useful because I can do E2 Stationowitz, derive some results and so on. But maybe from a perspective of modeling, I may actually want to see what is the effect of having a actual finite time correlation on my process. Right? Then introducing a finite time correlation is not so easy within E2 Stationowitz. It can be done, but I mean, it's not trivial. This is an alternative way of doing it, right? You can just live in the ODE world. So I can control that. Now, the last point I want to make is if you look at this function and you imagine I'm increasing k, I'm starting to go towards the white noise. So it's, in some sense, I'm trying to approach the zeta, remember? So if I take k going to infinity, what will happen is it will start becoming delta correlated. The correlations will happen at smaller and smaller time. But think about the variance, right? The variance is not changing. This variance is independent of, the variance of f is independent of k. But that is not the behavior of white noise. Remember, zeta is delta correlated with infinite variance at any time. That is what makes it non-differentiable as k goes to 0. That's not the case here, right? As I take k going to 0, there's no problem. I'm still smooth. The variance is staying the same. So to make it look like zeta, right, Trefethen introduces the same f of t, right, but divided by, multiplied by root 2. Again, this 2 is a normalization. The important thing is this lambda. So he divides it by root lambda. Okay? In other words, as lambda is made small, the variance is made to grow as 1 over root lambda. And he calls this a big, smooth random function. Okay, and the motivation for doing root lambda, can you guess? We've already seen this in our numerical integration of the very first assignment. Right? So remember in the first assignment, if I just generate a bunch of random numbers with some delta t, and then if I try to make delta t smaller, and I use the same Gaussian variance, it won't work. I have to divide those Gaussian random numbers by 1 by root dt. Correct? So this is exactly dt. So it's equivalent to dividing the random Gaussian time numbers by root dt. Only then it starts behaving like the Wiener process. Yeah, it makes sense, right? Because remember the ODE I'm going to do, so the reason I do this is so that, right, so this is done. Okay, so if I think now of the Brownian motion that I will get by integrating f, right? Now you can see that if the variance of f is kept the same, the integral is not going to converge if I use a normal random function. Why? Because the f will oscillate more and more. if you like, but then if I discretize it into pieces, right, the fluctuations are going to happen over smaller and smaller time scales. Right? And within an interval, it will average out. Right? Because see, this is going to be plus minus plus minus. If I fix my delta t and do the integral, and then I take a more highly fluctuating signal, within those delta t's, it will average out to 0 because it's random. So you will see that if I try to do this integral and I take lambda to 0, I'll just get the answer to be 0 because it will be fluctuating more and more. In any time steps I take to do the stepping, I will be averaging out all my force. It will become 0. Right? So this is what I don't want. Right? I want the integral to converge in some sense. So you can compensate for that increasing fluctuation by making the variance larger. That's one way to see it. The other way to see it is to think of exactly the Wiener process, right? Where I had the Wiener process is the normal distribution. The increments of the Wiener process is the normal distribution divided by root dt. When I do the, sorry, so when I should not say that, the zeta is the normal distribution divided by root dt, which we had seen in assignment 1. Okay, so again, we can test these things out in the code. Okay, so let's not worry now more about this formula, okay, but the main idea is that, so if you approach a stochastic system, right, SD, you want to get a feel for it, you don't want to get into Ito-Stashnovich immediately, you can replace it with an ODE where instead of the fluctuating stochastic part, you can put a highly fluctuating but smooth function, right? So that's what this smooth random function helps you do. Or alternatively, if you're modeling some physical system, right, it may be a particle moving, it could be some reaction process, and then you want to add in some noise, you don't necessarily have to go directly into the world of Ito and Stashnovich. You can just say, okay, let me add some forcing function with some prescribed amplitude and just make that function oscillate more and more in a random way. But how can I do this in a precise mathematical way? You can do it with this smooth random function. Then you can continue using your ODE solver. Okay. Suppose you're using some CFD tool, right, to do some fluid dynamics simulation, and you want to add some stochastic fluctuation to it. So any number of examples, right, could be there where you're maybe forcing a flow and then, or like say you're pumping a fluid, if you want to take a boring example, but there are some oscillations in the pump and you want to model those random noisy fluctuations, you just add some smooth random function and use your usual CFD simulator, for example, right? Because if you don't do this and you want to directly jump into Ito-Stashnovich, then you cannot use your CFD solver, right? Or it will be non-trivial to try to make that solve some SDs. Fine, so we'll return to some of those things later, but this is the logic, okay? And we can do it in this way. But now we're going to, let us first see how these functions work out. And then ultimately, the nice thing is if this works well, I can then look at the following problem, right? This is the Brownian motion, right? Or the normal random walk, right? And this, I mean, it will converge to this, right? Brownian as lambda goes to 0. This, right, should give me lambda going to 0, the geometric random walk problem. But the question is, in what sense, right? So now we have a concrete problem. I can construct this function f. This is a given ODE. I can simply integrate it, solve it, use Runge-Kutta, whatever. Okay, and I'll get some function of x. Since f is random, I can do many ensembles. And now I can check what happens to the mean, right? And what does this fluctuating, this ODE problem, as f becomes more and more fluctuating, what does it converge to? Does it become an Ito-like SD, in which case x will have 0 mean? Right? If I repeat this simulation for many, many different f's. If it becomes Stashnovich, then the x should grow exponentially. And my claim is that it will become Stashnovich. And this is very important because now you can see the connection, right? Because this is like a physical process. It's some model where you have some smooth but fluctuating forcing. And I can replace that fluctuating forcing with a Wiener process, but I will get Stratonovich if I want it to represent the correct limit. So let's see that in action now. Okay, so I want to direct your attention to the Mathematica code, okay, which you can see above, and those in the video should see it appearing on your screen. All right, so let's just look at this now. So I am doing this in Mathematica, but there is no particular reason to do this. You can easily use whichever software you like. Okay. And in fact, I will give you an assignment later which will involve this smooth random function, and there you could try to construct it yourself in Python or Julia or whatever. All right, so but Mathematica, one advantage is it's easy to read it reads like the math. Right? So let's go in. So what I'm doing here, so first of all, these are the papers that I based this lecture on. So the more detailed resource is this review article in the journal SIAM Review. Right? So SIAM is Society for Industrial and Applied Math. So in this article, they describe smooth random functions, its application to different kinds of random ODEs, and also something called Gaussian processes. But the full motivation that I did today is given there nicely, okay, for the smooth random function, the big smooth random function, the Brownian walks, etc., etc. This geometric example is not there, okay, but other nice examples are there. A simplified version of that article, right, briefer, without all the mathematical details, is in the following chapter, okay, Random Functions and Random ODEs, chapter 12, in the book Exploring ODEs. It's a nice book, published by SIAM, again by Trefethen and his co-workers. So this book is a general book about mainly ordinary differential equations, their nonlinear dynamics, bifurcations, chaos, etc. One of the chapters he deals with stochastic systems in this style. It's not a book about stochastic differential equations, but the important point he makes is, okay, if you understand the mathematics of ODEs and you have a stochastic problem now, you don't have to, at least to get some initial feel for your problem, you don't directly have to go to stochastic differential equations. You can live in the ODE world, but use this smooth random function. Okay, at least you will get some initial simulations. You can check, is stochasticity important before you start investing in trying to develop some stochastic model. Okay, so I think this is quite useful. Anyway, let's use it now for the purpose of our course. So here I am constructing a random function, which is basically my f of t, not the big one right now. Okay. So this is the f of t I wrote on the board. Okay. So I'm in Mathematica syntax, I'm creating a function. Okay, it takes two inputs, the lambda, which is this typical time scale, and L, which is the total length of the time series that I want. All right. Now inside, I use that capital L and I extend it, because remember, I don't want my forcing function to be periodic. I want to lose that periodicity, so I should generate it truly on a larger length and then cut it. So 1.2, because I'm going to look at very highly fluctuating things, even 1.2 is fine, okay, because the highest frequency will be like 100 times, right? So even 0.2 of L is maybe 20, 30 wavelengths more. And you can of course increase this, right? It's just a matter of how precise you want to be, okay? So fine, I take some length which is larger than L typically, and now I have to choose my largest mode number. So that is what I said, right? Floor of the total length of the time series, which is now the actual length I'm going to generate the periodic function on, divided by the time scale that I want to create, lambda. So lambda is an input, okay? And then m is calculated from that. And now I simply construct I generate the coefficients, right? So this function takes a random sample from the normal distribution with 0 mean and standard deviation, the following, okay, which is variance 1 by 2m plus 1. Okay. And I generate one such number for a0 and then m such numbers for ak and bk. Okay, so these are just the Gaussian distributed numbers with variance 1 upon 2m plus 1. And then I sum up all that stuff. Okay, I have my root 2 factor and so on. Okay. And this is the same definition, 2 pi k t by the total length. And k is this thing which sums from 1 to m here. Okay, so I've just defined the function just almost exactly like I wrote it on the board. And then to create this big version, which we will check whether it has use, I take this same thing and I multiply by square root 2 by lambda. Okay, so in other words, what this is doing is basically changing the variance of each of those k's, right, to be 2 by lambda 2m plus 1. Okay. And if you think about that, you will see that m itself is capital L by lambda. Right? So by adding this extra lambda, each of the AK's variance becomes independent of lambda. Right now, the variance of each AK depends on lambda through m. But when I do this extra thing outside, it removes that out. Okay, so anyway, so there are different ways of seeing this lambda. We will not spend more time on it. But I think the simplest way to think about it is like dividing by root dt. Okay. And so now I'm going to do some tests. Okay, so I'm going to take a time interval from 0 to capital 0 to 10. And let's first look at two different time scales, right? So lambda 1 is 1. So in the interval 0 to 10, I'm going to get fluctuations. Typically, there will be features on the order of 1. And then I'm going to get a much finer random function, 0.1. So that I've defined here in the code. Okay, so two different cases. Then what I'm doing is, so this is something that if you want to do careful tests, you should do, right? So each time I generate these random coefficients, it will generate new random things unless I control the seed. So I want to compare between different tests, right? I should fix the seed. Okay, so here I'm fixing the seed. And this I've already pre-run, so you can see the results here. So I have I'm just constructing two things and plotting it. So the first one is when lambda is equal to 1. Okay, and it's a random function. It's going up and down about 0. But you see, typically the variations are happening on a time scale of 1. Right? And when I make lambda 0.1, it becomes much more rapidly fluctuating. And then again, you see roughly that these things are on order now of 0.1. Right? So if you look at basically roughly if you bin it into units of 1, there will be order 10 fluctuations happening inside. So this is very nice. You can see it's clearly become more highly fluctuating, but the bounds on the signal, right, the variance is the same. Okay, by construction. Because I'm adding more random numbers in the bottom case, but remember the variance has decreased. Okay, so this is a nice way to construct a function which has the same variance but of increasing oscillation. But that is not going to mimic white noise, because remember white noise has infinite variance. Right? So to do that, I have to come to the big random function, which I simply take the above 2 and multiply by root 2 by lambda. If I now plot the same thing, again I can use the same seed, right? So it's the same. But the variance of the bottom guy is grown. Right? You notice the bars, axis range, right? So it went from -5 to 5 to like -15 to +15. It went like root of 10 because I divided lambda by 10. Right? So roughly 3 times it increased. So you can see that's exactly what that's what we built in, right? So at least this is just checking the mathematical code. Okay, so this looks nice, right? But you can already see now as I keep tuning the lambda, I can make it fluctuate more and more. Fine. Now what is the point? Let us now use this to solve random walks in the ODE framework, right? At least to approach it. Okay, so this code looks a little messy, but it's very simple. All I've done is solve dx dt equal to f. Okay, and that's what you can see here. And I did this for an ensemble of f's, so that I can then look at different trajectories and then average them out and get the mean and variance. Right? Basically, what we did in assignment 1, but instead of using Wiener processes and so on, I'm just using the smooth random function and actually solving it by ODE. And to make the point, I am not even trying to sum it up or anything. I'm just using ND-solve. So ND-solve is the mathematical equivalent of something like ODE 45 in MATLAB or solve IVP in Python or whatever. Okay. So you take your favorite ODE solver and you just plug in the differential equation, right? So here, that's what I've done here. I'm saying dx dt is equal to this f. Right? So I've called it f ensemble. So f ensemble is basically these big random functions. And I'm using the big ones because that's what we need to get convergence in the trajectories. We'll see that in a second. So basically I'm taking, this is f of t, but I'm generating 6 of them, right, just to get an ensemble of 6 f's. Right? That's I'm calling f ensemble. And then each of them I give one by one and I solve the ODE. So after solving this I'm solving 6 ODEs to get 6 Brownian trajectories. Okay, that's X ensemble. And now I'm just going to plot them, and I'm going to vary the lambda that I'm going to use to generate that F. Okay. So the results are shown here. So here I'm showing you an example of the, so this is for lambda equal to 0.5. Okay, I'm zooming into 0 to 2 and showing you what the signal, what a typical signal looks like. I've taken 4 such different signals to construct 4 different Brownian trajectories shown on the right. Okay, I'm just showing you one here to get the sense of the oscillations in F. So this is the forcing thing, which is tapping the particle. Okay, so here you have variations on the order of 0.5. And that, when you integrate from 0 to 10, okay, so this is 0 to 0.2, here it's 0 to 10, so it's extended. That's why it looks fluctuating more. But it's basically this integrated in time, right? And you see now that you get some kind of, it's random motion, but it's happening quite smoothly. So here also the steps, the undulations of the random walker are on order of 0.5 time. But now, so of course, if I zoom into this, it will look like a nice smooth motion. Now I'll make lambda smaller and smaller, right? So from 0.5, let's go to 0.1. You see, this has become more oscillatory now, and so has the trajectories. And now let's forget about this, just look at the trajectories, right? So I'm going from 1, it's very smooth, roughly 0.1, it's become sharper, still doesn't look like Brownian motion to the eye. 0.05, now you start seeing it starting to get this, right, highly stochastic character, which if you've seen Brownian trajectories I showed you in the first class, remember, it starts looking like that. And I can go even further, and now it really starts looking like Brownian motion. And of course, I can keep doing this down, right? I can 0.001 and so on. So the sharper you make it at a fixed, so the whole thing is you have to sit and look at it at the same resolution. Otherwise, if you zoom in to order lambda, it will always be smooth. Even the Wiener process doesn't make sense if you keep looking at things on the order of delta t. The whole idea is I'm staying order 0 to 1, and then I make delta t smaller and smaller. Then the Wiener process increments will give me results that will start to look like the actual mathematical SD. Otherwise, it's just a discretization. So same idea here, right? I have to stay from 0 to 10, and as I shrink the lambda, you start getting at least visually something, right? That certainly looks like Brownian motion now. And you see the different trajectories are random and doing things. Okay, so I can make this finer and finer, but it's fine. Let's quickly look at the, so I can do the same ensemble now with many more trajectories. So here I'm using 500 of them, okay. Repeat that calculation, and now sample the solution at some times and calculate the mean and the root mean square and plot it. Okay. So the blue curve is the mean, so that is the average of all those trajectories now, right? So like this I've taken 500, and at each time I'm averaging it out, right? So reasonably it's going to 0. Of course, that depends on the size of the ensemble, as you know, right? If you take very few, you will not be close to 0. As you increase n, it will converge to 0. And similarly, the root mean square does not converge to 0. It will converge to a curve that grows linearly in time. That's what's happening here, right? So you see, once the initial thing at long times, you have something that's definitely linear. Okay, so basically I'm getting Brownian motion. Now, of course, this is not a very rigorous check. You can, of course, use many more trajectories and calculate the diffusion coefficient, make sure that is 1. I mean, that diffusion coefficient of this trajectory matches the coefficient of f and so on, right? But already you can see that you're getting the behavior you want. Okay, now let's look at the geometric random walk. This is what this whole lecture has been about. So I use this exact same stuff that I did here, right, to get the normal random walk. But now what I can do, so this is the beauty of doing the smooth random function, right? Remember in the previous class, Brownian motion, okay, we knew that Gaussian is just summing up Gaussian increments. So the variance will grow linear like t. We could do easy math for the normal Brownian motion. The moment you say that the coefficient of the Wiener process is the function of x, that's when we got into a soup and we had to do all kinds of derivations. That's when the Ito calculus Stachnovich becomes different, right? That's when we had to show those derivations to get the Ito rules and Ito. All of that was just to deal with the fact that you can have a coefficient in front of the Brownian motion that's a function of x. Right? That's when the whole nightmare starts. If that coefficient is 1, then it is no problem. You're just adding up Gaussian numbers. Right? That's basic probability. But all the stochastic calculus has come in to deal with multiplicative noise, where the coefficient of the Brownian motion is a function of x. Now in this ODE world, nothing changes. I just directly put some whatever coefficient I like. So now instead of 1 here, right, which I had here, right, dx dt is equal to f. Now I have dx dt equal to x into f. Okay, and that's it, nothing changes. Of course, now if you put some weird nonlinear coefficient, right, nothing will change still, but your Runge-Kutta or whatever ODE solver will have to be able to handle that, that's all. You take sufficiently small time steps or something. So that's anyway given, but from a mathematical perspective, nothing has changed, right? You can just do the same thing. And so I expect a solution now, I plug this in. Importantly, I should not let x go negative. I mean, otherwise the geometric walk doesn't make sense, right? So I'm going to start x from 1. And then it should be fine. Then, I mean, if this makes sense, it should never become negative. That's what we understand in the limit, right, of highly fluctuating. Of course, if you make f not a highly fluctuating thing, of course it can go negative. The whole idea is this is geometric random walk which will always be positive if x starts out positive, only if this f is resembling white noise, right? Otherwise it is of course just a normal ODE, it can do whatever it likes. So provided my lambda is small enough, it should not go negative. Anyway, so I just solve this now. I do an ensemble again. And I calculate the mean and the variance, the root mean square. Okay. And now is the important thing, right? Remember, we derived in the last class, okay, which you can look back at your notes if you like, or those who are watching can go back to the previous video. So we derived there that the geometric random walk, right, has 0 mean in the Ito case, has exponential growing mean in Stratonovich. In both cases, the variance is going to grow exponentially. And now we expect to get Stratonovich because we are taking a correlated, it's still correlated, right? Lambda, I chose lambda 0.05. Something small but correlated. This should behave like Stratonovich. Again, that's exactly what we see. So of course, it's very, very noisy, right? 500 is not enough to resolve something like this, right, which is growing exponentially. So ideally, I would like to use maybe 50,000 trajectories, right? But that will, it took too long for me before the class, but we can do that at home. Anyway, so but the main test is not this, right? The test is the blue line going to converge to 0? So with the 500 ensemble in the usual random walk, right, it converged to 0. Now with the geometric random walk where I multiplied by x, if it was E2, it should have still been 0, right? But it is not. Not only that, it is clearly growing very rapidly. Ideally, I could have plotted this in semi-log and you would have seen it's exponential, okay? But I think you can also see here that it is increasing exponentially, right? So the blue is the mean, it's growing exponentially, and interestingly and importantly, the variance is also growing exponentially, but much faster, right? Because remember, the exponential growth rate was 4 times. Right? 4 times, I don't remember, some factor was there, factor of 2 or 4, correct? 2. So it is twice. This also sort of seems to have that. So ideally, what one can do, as I said, the assignment will require you to repeat this yourself and then apply it to other problems. So when you do this, you could plot this on semi-log, right? And then you will get straight lines, and from the slopes, you should get the exponential. But already for today's class, one can see that clearly this is not the Ito. Okay, and it's converging to, I mean, it tells you it's not Ito, but you can believe me that it is Stratonovich. Okay, so this is very nice. So what we are basically saying here, what Trefethen says in this nice article, right, is that as a first step, right, most of us, especially after basic engineering education, are familiar with ODEs and how to solve them numerically and their basic properties and so on, right? And we are comfortable with that. Right? So now if you have to deal with a stochastic system, to get initial insights, right, into your problem, what possible role it could have, whether it could potentially be important, or just to get some feel of things, you can just take the non-stochastic system, which is an ODE, right, and add a smooth random function to it in the place of wherever you want the noise to come. Okay. You have to be careful to take this 1 by root lambda, otherwise it will not represent white noise. Right? It will just be something else. Then you can't take the limit. So you can add this smooth function for some lambda, and you can make lambda as small as you like depending on your system, and already you will get some good insight. If your goal is purely to only get numerical results, then this is also perfectly fine, because in Trefethen's article he shows rigorously that it represents the properties of the Wiener process. Okay, so there is some math behind this, how these smooth random functions as k goes to infinity behaves, and there are some theorems and so on behind it. So it is not just some ad hoc thing, right? It has some mathematical basis. So one can proceed with this if you are only interested in numerical results. But if you want to now later say, okay, I want to prove something analytically or get some more firmer conclusions, then you can, okay, do the SDs. But at least you already have some sense of what's going on, right? And then you can, if it's really worth it, you can reformulate your problem as a stochastic differential equation in the Stratonovich framework, right? But you can see there will be lots of work involved in that. Right? So much before that, you can already get some insight. And as I said, it's easy to add to some existing code, right? You have some code which is for the deterministic problem. You want to add plus noise to it, you add plus smooth random function, right? Or multiply noise also, you multiply smooth random function. Right? So an example would be like you have air flowing over the surface of water, for example. You want to study the formation of waves. A deterministic formulation will keep a fixed air speed or air drag on top of the water, and you will study the problem. Now you want to say, okay, my air is actually turbulent, right? Now that's a big thing. I don't want to go and do a simulation of turbulence in the air and all that. At the leading order, does that matter, right? Can I just put the mean airspeed on my water layer, the mean air drag on my water layer? Is that good enough? Or do the fluctuations do something very different, right? Completely change the nature of the waves, for example. So a simple way to test this is you take a deterministic model, and wherever the air drag is coming, you add smooth random function, which has zero mean and whatever variance you decide to give. And then you can control how the fluctuations are. Of course, if you make smaller and smaller lambda, smaller and smaller fluctuations, you will have to take smaller time steps in your ODE solvers, right? Or PD solver, whatever. Right? But that's okay. It's still a matter. It's still much easier than trying to completely reformulate the problem, at least as a first introduction. And it also lets you play around with and to gain some insight or some support for thinking about the stochastic results that we have derived, right? Which are not so easy to get our minds around. So even yesterday's class, the fact that Ito and Stratonovich changes the mean, right? One can do the derivation, but it's difficult to get a feel for it. Using such things, it's easier. So later on in the course, as we get more results, you can come back to this kind of tool, right? And use it as a tool to understand and to learn, right? Even to get more confidence in any derivation you do. All right. So that's what we'll do. Later on, it should be maybe the fourth assignment. We'll use these smooth random functions. Okay, we'll stop for today. Thank you.